Hi, this is Massimiliano, and this is a presentation based on the PowerPoint of a talk I gave on May 16 of this year in Paris at the headquarters of European Space Agency in the ambit of their Beyond Space series, whose scope is to present to their staff ideas going beyond space as such. So this is a presentation aimed at a rather diverse audience of people, hence also accessible to non-specialists, as long as they are sufficiently curious, of course, about science and its foundations. So, is reality in space? Well, it is generally taken for granted that our physical reality would be fully contained in space. However, phenomena like quantum entanglement, quantum interference effects, and quantum indistinguishability, when taken seriously, tell us a different story. That there would be much more in our physical reality than what meets our three-dimensional eyes. So, is reality contained in space, or is space just a very small theater for a non-spatial reality? And if the building blocks of our physical reality are non-spatial, what does it possibly mean? Well, in this presentation, I will try to answer some of these questions. Let me start with Plato's cave allegory. According to Plato, we are like prisoners chained from time immemorial in a dark cave, only watching and studying shadows flickering on a wall, and thinking that those shadows and the wall is all of our reality. In Plato's allegory, you have the ontological level, which is the level of the real objects, which is considered to be that part of the world that is unperceived by our ordinary senses, but that somehow can be understood by our intellect. Then there is the empirical or spatial-temporal level, which would be the level of the appearances of these real objects. Another interesting allegory is that of Abbott's Flatland novella. It was written by the English schoolmaster Edwin Abbott to criticize at the time the Victorian culture. It was back in 1884. Now, according to Abbott, we are like the residents of a flatland, that is, low-dimensional beings living in a thin layer, so to say, of our reality that can be traversed by entities of higher dimensionality. Let me give you an example. Imagine being a wingless insect living at the surface of a lake, and that a three-dimensional entity of the upworld, say a human hand, dips its 5 fingers into the water. From your limited perspective of a two-dimensional being, well, here almost two-dimensional being, you will see appearing out of nowhere 5 strange ephemeral entities which you will certainly imagine be separated and independent from one another. But from the perspective of a three-dimensional entity of the upward, it is clear that these 5 entities are just the traces of a fully interconnected whole entity, the human hand. So how did we construct our spatial theater? This is a good, important question to ask in the first place. Well, as an evolving species, we have been present for hundreds of thousands of years in a very special niche of our reality. That is the crust of our beautiful planet Earth, the pale blue dot, as Carl Sagan used to call it. We have been surrounded by very special physical entities, and from our multiple interactions with these entities, which we experience by means of our dense and microscopic bodies, we started a long time ago the construction of a prototypical worldview in the attempt to order our experiences into a consistent map of relation. And to do this, during this pre-cultural and pre-scientific time, we have been, so to say, penetrating reality along 2 different directions, an in-depth direction and an in-width direction. So what is penetration in depth? Well, by penetrating reality in depth, we have identified those phenomena that, according to our senses, and in particular the sense of sight and touch, which work together pretty well in a pretty synergistic way, so we have identified those phenomena that stood out compared to others because of their persistent availability in interacting with our bodies and becoming a stable part of our experiences. In this way, we have recognized the existence of experientially separated and stable portions of our reality, today simply called classical entities or macroscopic objects, obeying, I mean, these are the objects which obey with good approximation the laws of non-relativistic classical mechanics. And of course, they include the astronomical bodies that we can see moving in the sky, like the moon and the sun. Now, on the other hand, penetration in width corresponds to our effort to organize the content of our experiences with all these different aggregates of stable properties, these objects that appear to us to be separated in the sense of not influencing each other in a significant way. And this can be understood as an ordering process precisely giving rise to a space. And since most of our experiences were with classical entities, with macroscopic objects, the space of relations that emerge in this process is what we call today the three-dimensional Euclidean space. So space can essentially be considered as a theater of reality that emerged when a given subset of experiences was properly ordered and organized. But can we fit all of our possible experiences with all possible physical entities in this three-dimensional Euclidean space, theater, which over time, by the way, we have mistaken for a fundamental substantive container for the whole of our physical reality? Well, we have to understand that new experiences were accessed in more recent time in controlled experimental contexts, which are very different from those we experienced during our pre-scientific and pre-cultural process of penetration of reality. And we have these new experiences with entities that stubbornly do not lend themselves to be easily included in the relational space theater that we have built to stage our entire physical reality. In other words, following the discoveries of modern physics, the hypothesis that reality would be fully contained in space, as I'm going to try to convince you now, can no longer be supported. Now, the paradigmatic example of the breakdown of the Euclidean theater construction is the discovery of so-called quantum entanglement. Now, at the theoretical level, entanglement was initially discussed by Einstein and Schrödinger back in 1935. Its existence has been now established in many experiments, starting from the historical ones performed by the French group of Alain Aspect with photons in 1982. And of course, more recent experiments today have closed all possible experimental loopholes. Now, what is entanglement? Well, a two-part entity, a composite system formed by two parts, is said to be in an entangled state if it can have its two parts possibly spatially separated by arbitrary distances, but nevertheless remaining experimentally and invisibly connected. And this fact, this possibility, is clearly incompatible with our spatial construction, because the notion of spatial distance was precisely used also to quantify experimental separation, in the sense that the greater the spatial separation between two entities, the lesser their mutual influence should be. This is sometimes called the principle of locality. Okay, but how is entanglement revealed? Well, we reveal entanglement by studying the nature of correlations that are produced by coincident experiment or joint measurement. Now, it's important to distinguish two different kinds of correlation. According to Diederik Art's classification, we have correlation called of the first kind, and these are the correlations that are only discovered during the measurement, and they cannot violate so-called Bell's inequality. On the other hand, we have correlations of the second kind, and these are correlations that are literally created during the measurement and will generally violate so-called Bell's inequality. What are these Bell's inequalities? Well, in 1964, John Bell discovered a particular inequalities, nowadays called, Bell's inequality, and these inequalities only involve quantities that are experimentally accessible, probability essentially, but are able to test if the observed correlation were already existing prior to the joint measurement, hence were only discovered by the latter, or if the correlation were only potential prior to the joint measurement, hence were literally created by the latter. Okay, to clarify things, let me give you an example of correlation of the first kind. The famous example is that of Bertelsmann socks. It was given by John Bell himself. So Dr. Bertelsmann was a colleague of Bell, and he liked to always wear socks of different colors. Which color he will have on a given foot on a given day, was quite unpredictable. But when you see that the first sock is pink, you can already be sure that the second sock will be not pink. So observation of the first Bertelsmann sock gives immediate information about the second. But the color of the two socks is clearly not created by their observation. Hence, they pre-existed the observation. And so this is an example of correlation of the first kind, not able to violate Bell's inequality. Can we then give a simple example of correlation of the second kind, which would be characteristic of quantum entanglement? Okay, yes, there is a very simple example, and this is the following experiment, the experiment of breaking an unbroken elastic band. Imagine two people pulling the two ends of an elastic band, and let me call them Alice and Bob, as is tradition in physics. And now if they pull the elastic band and they break the elastic band, the process will create correlation, which were not existing prior to the breaking of the elastic, and in a totally unpredictable way. And this is a typical situation of correlation of the second kind. So we have Alice, Bob, they pull the elastic, it will break somewhere, it's unpredictable, so all sorts of outcomes can be produced. Here you have 3 examples. And of course, all these outcomes are correlated in the sense that the length of the fragment, elastic fragment of Alice is correlated with the length of the elastic fragment of Bob, because the sum of their length, of these two lengths, always have to give back the total length L of the unbroken elastic band. So, let me remind here something important. Quantum observation or quantum measurements are processes that can create properties that were only potential prior to the observations. This is sometimes called the observer effect. So, as a consequence of that, when observations are performed on composite entities in entangled states, they can create actualized correlations that were only potential prior to the observation. The joint observation creates properties that are correlated, so they create correlations. And this is a situation, of course, such that Bell's inequality can be violated. So, example like this one of breaking elastic band is not just, let's say, a didactical example. It's also important because it demystifies the idea that entanglement would be characteristic only of microscopic systems. While also ordinary macroscopic entities can be entangled, like elastic bands that can be broken, or dies that can be connected, for instance, by means of a rigid rod that can be rolled together, or vessels of water which can be connected by means of a tube. This was an historical example provided by Professor Diederik Arts. So all these examples are examples of entangled entities. But here, I mean, the reason why we have this entanglement situation, that is a situation that is able to create correlation, this is clearly due to the fact that there is a connection, and that this connection, we can see it, so there is no mystery here, because it is a spatial connection. So, also macroscopic entities can violate Bell's inequality if only the joint measurements can actualize potential correlation, which will generally always be the case if the composite system forms an undivided whole. That is, its components are connected in some way. And here the way is a way through space by means of some element of reality. Okay. Now, what's the big difference between example of this kind and what is referred to as quantum entanglement in the micro world? Well, the big difference is that quantum entanglement with microentity is, it's the expression of a connectivity which is not in space. Connections that are characteristic of quantum entanglement cannot be represented in our three-dimensional Euclidean theater, nor detected. There is nothing detectable in the space between two spatially separated entangled entities. No detectable spatial connection, but the two entities can still influence each other at a distance, or it would be more correct to say they can really behave as if they are part of an undivided whole entity. We must thus conclude that quantum entanglement expresses a form of connectivity that is not in space. So, microscopic entities would generally not be in space, but would be brought into space only when interacting with measuring apparatuses, or when, of course, forming macroscopic aggregates in standard conditions. And since entangled states are the vast majority of states, we have to conclude that the vast majority of our physical reality is non-spatial. And by the way, the fact that entanglement is a non-spatial phenomenon can be seen by the fact that, being not affected by definition by spatial distances, records of distance in the creation of entangled entities are constantly broken. So in 2012, an international team was successful in obtaining entangled photons over a distance of 143 kilometers between the two Canary Islands of La Palma and Tenerife. And more recently, in 2017, China's Mixiu satellite was able to send entangled photons to two different stations on planet Earth, separated by a distance of 1,200 kilometers. So this is clearly, a description of a phenomenon which absolutely does not depend on spatial distances. Okay, but someone could object that, well, maybe when microentities are not entangled, they would be, maybe in this case, fully in space. That is, they would behave as bona fide spatial entities, like particles and waves, depending on the context. Well, maybe it's just entanglement which is non-spatial, but when entities are in separated states, they are again in space spatial entities. So this is a view that cannot be considered, and we can give example why even single entities have behavior that are really non-spatial. So I take the example of the spin of a microscopic entity, like an electron or a neutron. What is spin? Well, spin is a kind of intrinsic angular momentum which behaves like a micromagnet, sort of magnetic dipole with a north and south pole. Now, if you take a spatial entity like a magnet and you rotate it 360 degrees, the rotation will bring it back exactly to the same state. Now, if spin is something like a magnet, or if not really a magnet, but at least something having a direction in space, which usually we can attach a direction in space with spin. So we would expect, if spin has this direction spatial property, that if we rotate a spin 360 degrees, it would come back to the same state, which is not the case. We really have to rotate a spin twice, 720 degrees, to be able to bring it back to the same state. Now, this was something which was very well known at the theoretical level, and for quite some time physicists were wondering if this was an actual property of spins or just a theoretical artifact. And in fact, beautiful experiments were done back in the mid-70s of past century by two groups, group of Helmut Rauch and the group of Samuel Werner. And these are experiments using neutron inside a device made of a single silicon crystal, a so-called LL device. So as you can see on the figure, this is a device which is, approximately 7 centimeters in size, and it has 3 blades, parallel blades. So neutron comes from a source, and when they arrive at the first blade, because of the particular geometry of the crystal, they can either pass through the blade without being deflected, or they can be deflected of a given angle. So only these two possibilities can happen, and so there is a bifurcation each time a neutron crosses one of these blades. So you will have, therefore, all these paths that are depicted here on the figure, and we will just consider the two internal paths, and we will do as if the external one are not there, because they are not important and they will just complicate the discussion. So let's do as if only the internal path here represented in red are happening. So you see that these paths recombine at the level of the third plate, so there is a superposition of the beams, and then in the end they are detected by the detectors D2 and D3. So the experiment is about placing a highly localized static magnetic field on one of these two paths, and the reason for doing that is that the magnetic field will rotate the spin of the neutron, and the more by increasing the intensity of the magnetic field, we increase the rotation angle, because there is by means of a phenomenon called of Larmor precession. Now, what is remarkable is that when the strength B of the magnetic field is varied, the spin rotation increases, and the measured intensity at detectors D2 and D3 exhibits a remarkable 4 pi modulation. So the intensity is not constant. Of course, there is an interference effect because the two beams superpose, but the variation of intensity is a periodic function where the period is not 360 degrees, but 720 degrees, that is 4 pi. So this really shows that the magnetic field strength has to be such that the rotation is twice a full rotation if we want the intensity to come back to the same level. So this really proves that a spin of a neutron has this, let's say, property which we cannot think about. So we cannot think about the direction of a spin as a direction fully in space, because we need this double rotation to bring it back to the same state. But in fact, these experiments are much more remarkable than what I have just said, because something very important that I have not mentioned so far is that just a single neutron at a time passes through the device. So these interference effects that were observed, these were really self-interference effects. It was really a single neutron interfering with itself. So this is very important to observe, because it has important consequences on how we can really think about this neutron. So let me here rescale the experiment 25 millionth time. If I do so, you will see that the single neutron so as I said, a single neutron at a time enters the device. So the neutron enters the first, pass through the first plate in Paris, then it is, of course, deflected. It can go either south or north. We have the two paths. Now, on the northern path, which is approximately where Sweden is, the magnetic field is applied, whereas the northern path passed through Poland, so hundreds of kilometers of distance, and then they recombine, of course, approximately in Latvia. Now, what is important here to observe is that a neutron has a so-called coherence length, and when we rescale 25 millionth time this coherence length, we see that a neutron is typically an object of 25 centimeters of size. So it's very small. I mean, these paths are really very narrow. So we would be tempted here to say that, okay, but then a neutron, it's really much like a projectile, a corpuscle. It's more like a particle, really. But this cannot be considered to, we cannot assume it to be a particle, because if it was a particle, then of course we would not be able to observe interference effect. Because if it was a particle, then it would either go south or either go north, so there would be no possibility to have an interference effect, and the two detectors would click on average exactly the same number of time. So it is not a projectile because we observe this interference effect, but it's also not a wave because, of course, the neutron remains very well localized along this path. There's nothing in between them. So we really have to go beyond the naive idea that the neutron would be something like a particle or something like a wave. It's neither a particle nor a wave, so we really have to go beyond this wave-particle spatial duality. So we see here a behavior which is a non-spatial behavior. And this, of course, in this experiment, since one neutron at a time enters the device, this experiment has nothing to do with the idea of entanglement. So it's not about entanglement. It's really about the fact that the neutron behaves as a non-spatial entity, which is able somehow to sense both paths, both, trajectories, but it's not really on one of these two trajectories. So its behavior is really, in a certain way, puzzling. Now, you may ask, okay, do we have an example of an entity which we can think about, which behaves a little bit similarly to this weird neutron, which is able somehow to be on both paths and in none of them at the same time? So let me give you an example that I heard the first time when I was assistant in Geneva of Professor Constantin Piron, one of the founders of, at the time, very famous Geneva School of Quantum Mechanics. Now, to his students, he would propose the following example. It was with Swiss francs at the time, so I will do it now with euro. So take a 10 euro bill. When it is intact, we can say that the 10 euro are located somewhere in space, like a classical entity. Well, they are located exactly where the 10 euro bill is located. But what happens if the bill is torn into two parts and the obtained two pieces are spatially separated and placed into two different boxes? Well, when this happens, we cannot say anymore that the 10 euro are still located somewhere in space. Although we cannot even say that they would have completely disappeared from space. If we look in a single box, the 10 euro bill, we cannot say that it is present in a single box because there is just a fragment of it. On the other hand, the 10 euro, if we think of the 10 euro as a conceptual entity, then it is kind of simultaneously present in potential terms in both boxes. And of course, when the two fragments are recombined, the 10 euros conceptual entity are brought back into the spatial theater also as a concrete paper bill object. Okay, so let's keep this example in mind, and let me now describe another quantum property which is remarkable and points to the idea that quantum microentities would be non-spatial, and this is indistinguishability. Now, think of spatial entities like billiard balls or our physical bodies and all objects, surrounding us in our everyday life. So these spatial entities some of these spatial entities can be identical, at least in principle, but they will always be distinguishable. Why this? Well, because if we assume impenetrability of two identical physical objects, they can nevertheless always be distinguished, by considering the fact that these objects are following different trajectories in space. So we can always use these trajectories in space of two otherwise identical objects to label then these objects. So the trajectory in space with the spatial properties can be used as labels to distinguish the different entities. Now, if quantum microentities like neutrons would be non-spatial, as I'm trying to convince you, well, then we certainly cannot use their trajectory anymore to distinguish them. So they should be truly indistinguishable, even though they can also, strangely enough, remain individuals. Well, they can remain individuals because they have attributes that can be measured and used to count how many of them are present in a given system. For instance, if the total electric charge of a collection of electrons is Q, knowing that a single electron has charge E, then we know that the collection must contain a number n equals Q divided by E of identical electrons, because these charges adds up. And so, by measuring the total charge, we know that we are in the presence of not a single electron, but of an entire collection of them. Okay, so now what is important here to observe is that indistinguishability affects the statistical behavior of identical entities. Hence, it has experimental consequences that have been observed in countless experimental situations. So, quantum microentities are indeed truly indistinguishable, and this fact the fact that they are indistinguishable has experimental consequences that have been observed. So it's not just a theoretical hypothesis, it is a fact. We are in the presence of entities that cannot be distinguished. But on the other hand, they remain individuals, so this really cannot be understood if we think about them in terms of spatial entities. So let me just be a little bit more specific here, just to explain you why the statistical behavior is affected by the fact that entities are distinguishable or indistinguishable. Assume a very simple situation of two entities, A and B, and let me assume that they can only be in two different states, psi and phi. So if they are distinguishable, if they are like classical entities, then the composite system formed by them, assuming that the two entities are not interacting, not to make things too complicated, then we can have a total of only four different states. You can have the situation where the two entities are in state psi, the two entities are in state phi, or one entity is in state psi and the other in state phi, or the other way around. So a total of four different configurations. So when we count these different configurations, we are counting things at the Maxwell-Boltzmann way, in the Maxwell-Boltzmann way, the classical way. So classical statistical mechanics is built using this way of counting. Now, if you assume that entity A and B are identical, then the last two situations cannot anymore be distinguished. And therefore, when you count the different possible configurations, you only have now three different possible configurations. And this way of counting is called the Bose-Einstein way of counting and is characteristic of so-called bosons, entities having an integer spin. And you also have another possibility, which is called the Fermi-Dirac way of counting, where you just, in this simple example, you remain with a single configuration. And this is in the situation for those entities which are called fermions, which having a fractionary spin and obeying also, in addition to all that, the Pauli's exclusion principle, which does not allow two identical entities of a fermionic type to be exactly in the same state in the same moment. Okay, so as I said, all this has consequences. Just to give an example, the spectrum and intensity of so-called thermal radiation, the radiation emitted by a non-reflective body, a so-called black body. So a body having a given temperature will emit a radiation which is a function of this temperature, and the intensity and spectrum of this radiation as a function of its temperature. Now, if we consider how the behavior of this emitted radiation, then this can only be explained by considering that all photons involved in the energy exchanges are generally indistinguishable and therefore obey the Bose-Einstein statistics. And the black body radiation was one of the difficult problem that physicists had to solve at the beginning of last century and which was at the origin of quantum mechanics. Okay, so there is truly, quantum entities are truly indistinguishable. So how can we understand now, again, the nature of entities, non-spatial entities, but are able to remain individual, so and at the same time are also truly indiscernible? So let me give you again the example of the concept euro. So imagine you have a concept euro. Now take a certain number of these concepts, say 10 of them, and how you do that? Well, in the human conceptual realm, a collection of this kind of can be described by simply considering the conceptual combination 10 euros. So it's a combination of two different concepts, a numeral and the noun euro. So clearly all the euro concepts in the 10 euros combination are perfectly identical and all exactly in the same state. They are all carrying exactly the same meaning or the same value also. At the same time, we are truly in the present here of a collection of entities and not of a single entity. So the fact that 10 euros is a concept and not a spatio-temporal object is absolutely crucial for it being able to carry the otherwise puzzling quantum theater of being many and at the same time being generally indistinguishable. Okay, now one may wonder at this point if that of the 10 euro could be more than just a clever metaphor or example and actually point to a deeper truth about our physical reality. The possibility that its building blocks would not be object-like, but more something like concept-like. In other words, one may wonder if quantum entities would behave similarly to human concepts because in fact they would share with them the same conceptual nature, and two, human concepts would behave similarly to quantum entities because in fact they would share with them the same quantum nature. Now, could it be that quantumness and conceptuality are just two different ways of speaking about the same reality? Now, regarding point 2 above, it is much less controversial than point 1, and it is related to a field of investigation that developed in the last 2 decades and is called quantum cognition. What is quantum cognition? Well, it's according to quantum cognition, phenomena such as information processing, decision-making, concept and conceptual reasoning, concept combination, human judgment, and so on, these are all quantum-like, all these phenomena, in the sense that they all exhibit a quantum organization. Okay, so this is so on the other hand, point 1 is a question that was addressed in 2009 by Diederik Hardt, who, by the way, is one of the pioneers of quantum cognition. Diederik Hardt has been working a lot with this idea that human concepts can be properly modelized by using the quantum mathematics and the quantum notions, and by doing so for a long time, at some point, he started asking a deep question, which is the following: if quantum mechanics as a formalism models human concepts so well, perhaps this indicates that quantum particles, so to say, themselves would be conceptual entities. Is it possible? And now the answer he gave to this question it's called the conceptuality hypothesis, and it's a bold answer, of course, a bold hypothesis, which says the following: the nature of a quantum entity is conceptual, that is, it interacts with a measuring apparatus or with an entity made of ordinary matter in an analogous way as a concept interacts with a human mind or with an arbitrary memory structure sensitive to concept in the sense of being sensitive to the meaning carried by concept, because concepts are meaning entities. In other words, the elementary microscopic entities which cannot be consistently described in terms of spatial notions like particles, waves, and even fields, would nevertheless behave as something very familiar to all of us, as we continually experience them in a very intimate and direct way, concepts. But of course, immediately here, a warning is necessary. Quantum entities would be conceptual only in the sense that the notion that gives rise to the way of being of quantum entities and human concept would be the same. So we don't have to produce here two easy anthropomorphisms. If we consider the example of an electromagnetic wave and a sound wave, a sound wave and an electromagnetic wave are very different phenomena, very different physical entity. So nobody would mix them up. But of course, they nevertheless share the same wavy undulatory nature. So the same is true, would be true here for microscopic entity and human concept. They are very different, but they would share the same conceptual nature, which explain why they would behave in a similar way in certain context. Okay. Now maybe, okay, this presentation is not about the conceptuality interpretation per se, but so of course this would, I mean, it would require a lot of time to explain all these things properly. There are many subtle things to be explained. But let me just point to something important which will somehow help you to better understand why this conceptuality hypothesis can make sense. And this is the fact that concepts, like physical systems, they can be modeled as entities that can be in different states. I'm speaking here of human concepts. There is a way to model human concepts as entities that can be in different states, and this appears to be probably the more advanced and way to model concepts, because the ancient way to model concepts, this was to think about concepts as sort of containers of objects. This goes back to Aristotle. But this way of doing presents all sorts of problems, and in fact more advanced ways to really think about concepts as meaning entities that can be in different states. So let me just give a very simple example. Take the concept car. So when you just consider car in the context of itself, car is a meaning entity in its most neutral possible states, sometimes referred to as the ground state of the concept. But then we can take car and combine car with another concept, for instance, the concept fast, in the sentence a fast car. So when we do that, we change the meaning of car because we surround car with other concepts. And this will produce a change of its state. So combining concepts together, this is something we do all the time when we use our human language and when we communicate, because these kind of combinations change meaning and create new meaning. So in this example, so when we go from car to a fast car, we change the ground state of the concept car and bring this state to an excited state, so to say. And so this would be a deterministic, in this case, change of states, a little bit like when the neutron was passing through the magnetic field and its spin was rotated of a given angle. Now, there is a way to test the difference of these two states, and this is, for instance, to consider two example of car, a Volkswagen Beetle and a Lamborghini Countach, and ask a group of persons to tell what is the best example of car. If Volkswagen is a better example, Volkswagen and Lamborghini, which one of these two is a better representative of car? And so, for instance, in this situation, if you ask them in relation to car, that is, in relation to the ground state, probably a comparable number of people will choose the Volkswagen and the Lamborghini. I've not done the experiment, but I was guessing, let's say, that 60% will say Volkswagen and 40% will say Lamborghini. But now if you ask the same question, but with the same group or a different representative group, but this time in relation to a fast car, so we are now using the excited state, then the probability for the two different outcomes will be very different, because almost everybody will now choose the Lamborghini as the best representative of a fast car. So you see, a different state for the concept will produce different outcome states when the concept is subjected to an interrogative context, which is a measurement context. And this is exactly what happens also in the physics laboratory when we perform quantum measurement. Different states produce different probabilities for the possible outcomes. And these processes of selecting an outcome are, of course, indeterministic this time. Okay, so I hope this explains why it's meaningful to think about concepts as entities that can be in different states, and therefore why also physical entities can be considered to be conceptual. Okay, so now let me very briefly tell you why the conceptuality interpretation allows us to understand the non-spatiality and other strange property of the quantum entities. So what is non-spatiality? I mean, what does it mean that an entity is non-spatial? Well, according to the conceptuality interpretation, quantum entities can be in non-spatial states because as conceptual entities, they can be in states having different degrees of abstractness or of concreteness. And only the maximally concrete state correspond to those belonging to our three-dimensional spatial theater. So non-spatiality is about abstractness. So if physical entities are concept-like, they can be in states that are more or less abstract, and this explains what non-spatiality is. It is a state of abstractness. So take, for example, the concept thing. So this is very abstract. Now, if I combine the concept with other concepts in the combination, the thing as a car, the thing concepts start entering a state which is a little bit more concrete. Then if I increase the number of concepts combined, then like in the thing as a car called Lamborghini concept, this is even more concrete. And I can also increase, so I'm start telling, more and more stories. So the things as a car called Lamborghini contact that is owned by my neighbor. So I am increasing the length, the amount of concepts which are combined together, a little bit in the same way that a macroscopic body is formed by a huge number of concepts. So in this way, I little by little bring the concept in a much more concrete state, which then can be also in a correspondence with a three-dimensional macroscopic object, which we can encounter in our everyday life. So this just to give you the idea. So non-spatiality would be something to be related with the idea that concept can be more or less concrete or more or less abstract. And this immediately brings us to the Heisenberg, so-called Heisenberg uncertainty principle, which, roughly speaking, asserts that you cannot jointly determine the values of quantities that are said to be canonically conjugate. You cannot determine them jointly with high precision, and the typical example is that of position and momentum. So if quantum entities are conceptual, then they certainly cannot be simultaneously in a maximally abstract and maximally concrete state. And Heisenberg uncertainty principle, according to the conceptuality interpretation, would be nothing but an expression of the unavoidable trade-off between abstractness and concreteness, in the sense that the more we increase the former and the more the latter will decrease, and vice versa. So take the example of a neutron. If a neutron has a well-defined momentum, well, then it will be in a maximally abstract state, whereas a neutron with a well-defined position would be in a maximally concrete state. And all states in between these two limit situations, so-called superposition states, would be non-spatial states having an intermediary degree of abstractness or of concreteness. So we really see now that this conceptuality interpretation allows us somehow to start really understanding how is that possible, why Heisenberg uncertainty principle expresses something fundamental, and non-spatiality is, a property that is, really characteristic of quantum entities, because all concepts will be more in general in very abstract states. What about entanglement? Well, if the nature of the microentities is conceptual, then the non-spatial connections that are responsible for the creation of correlation in joint measurement, well, would be nothing but connection through meaning. Because, of course, conceptual entities are expected to spontaneously and systematically connect by sharing meaning. And since meaning connection are complex abstract elements of our reality, this also explains why they cannot be represented as simple spatial-like connections detectable in our three-dimensional theater. So quantum entanglement is meaning connection, and this also explains why quantum entanglement is so ubiquitous everywhere. As soon as you allow two entities to interact, we will immediately entangle. And the same, we understand that this has to be like that because concepts always share meaning. And of course, depending on the context, they can share more or less meaning. And of course, if they share sufficient meaning, they are able then also to violate Bell's inequality. And in fact, this can be shown to be the case when we do experiments which are similar to the experiments we do in the physics laboratory. We can do experiments in the psychological laboratories. We can have people subjected to composite conceptual entities, having to answer questions, and then we can study the correlation of this question, and we can see it's possible to demonstrate that Bell's inequality are also violated in the psychological laboratory. So this gives, of course, more support to the hypothesis that quantum entanglement would be a meaning-like connection. Okay, and the indistinguishability, we have already mentioned that. Of course, we have this example that in the human conceptual realm, indistinguishability is something which is perfectly self-evident, and this because we have so-called numerals and count nouns. Count nouns are those concepts that admit the plural form, which means that they can combine with numeral concepts to form a composite entity describing perfectly identical entities, which are nevertheless able to remain individuals. And also this, one can do experiments and check that indeed by counting how many times certain combination of words appear on documents, we can check, and remarkably, that this way of countings that emerge is more of the Bose-Einstein kind than of the Maxwell kind, Maxwell-Boltzmann kind. So we really find quantum statistics in human conceptual realms. Okay, I will stop here because, of course, many other fundamental problems of physics can receive interesting insights from the conceptual interpretation, but we cannot address everything in a single presentation. So let me just now take the time to conclude. So I started with some ancient allegories, telling us already at the time that our spatial theater is too limited, and I also try to convince you that, according to certain experiment of modern physics, we already somehow we can point to the same idea than what these ancient allegories already try to tell us, even though, of course, there is a difference in the sense that when we consider quantum entities, well, quantum entities do not really cast a shadow on our three-dimensional spatial theater. Things are much more complex, and this is because of indeterminism, because potential properties are actualized in a way that each time is different. So there is it's not a deterministic process like an object casting a shadow, but it is more something like more a symmetry breaking process, where the actual breaks the symmetry of the potential. So it's the image of these ancient allegories is insufficient to account for what really we have observed in the physics laboratories. Now, I mentioned quantum cognition and how quantum cognition allows somehow to ask the question that was asked by Diederik Atz some years ago, which brings us to the hypothesis that physical entity would be conceptual. So this is the conceptuality interpretation of quantum mechanics. And so according to this interpretation, we are using the wrong image when we try to capture the nature of the physical entities. We think of them in terms of objects instead of concepts, non-human concepts, of course. Now, it would be then our more recent and abstract way of interacting with reality, guided by language and meaning, which appears to be the one able to bring us closer to its deeper aspect, which are generally non-spatial and most probably conceptual in nature. And from the idea that the building blocks of our physical reality would be conceptual, entities carrying meaning and exchanging it with the different pieces of ordinary matter, a natural pan-cognitivistic view, of course, emerges, which has some deep consequences also for our understanding, for instance, of evolution. Indeed, the notion of quantumness would then interlace with multiple aspects of our world, including the appearance of the complex life forms on the surface of our planet. But of course, as the French would say, affaire à suivre. So let me just give you a few references, and thanks for listening.